Recording. Are you recording already?
Yes.
Okay. Okay, so let's see. Okay, the rest of this you will have, I don't know what happened. I lost some information here, but anyway, you notice, I hope you will be able to complete this in the homework, don't worry. Now, let's go to this, you have to review it before class. So please, I need somebody to tell me his or her equation of motion. Anybody? Somebody. You have to deduce, you have to do this before class. So here, you are supposed to have it at hand, okay? So you are supposed to have it now. Okay, let's go on. Miss Matias, what's your equation of motion, please? Miss Matias, did you deduce the equation of motion? No? Miss Matias, are you there? Oh, Miss Matias, your microphone is off. Okay, now talk. Tell me your equation of motion here. No, you don't want to tell me. Good. Okay, Delgado, Mr. Delgado, can you tell me your equation of motion?
I am doing, doctor.
Oh, come on. You are supposed to do it before class. Gutenberg, where are you right now, Gutenberg?
In Ibarra, but the next week I can travel to Guayaquil.
Okay, tell me, what's the equation of motion? Did you do it?
No, not yet.
Shoot. Okay, do it now. Okay, does anybody has it? Otherwise, I will let you work right now. I'm not going to do it for you. Do it for you. Jimenez, you have it?
Oh, yes, doctor. For the equation of motion is m per w dot plus k sub 1 plus k sub 2, both between, yes, per b, sorry, wb, plus k sub 2 per bay minus k sub 1 per a per theta, right, equal to 0.
Okay, good. And the second one?
The inertial acceleration plus acceleration mod per b, k over k sub 2 per v minus k sub 1 a bay per wv plus k sub 1 a to square plus k sub 2 b to square plus equal to 0.
Okay, so that's the first step.
Yes. Okay.
Here, we have a special situation, okay? We are taking these moments with respect to an axis through point C. See, the centroid is here. We are taking this, okay? Okay, in the case of the ship, we can do it, but it's gives us a very hard time because in every loading condition, the centroid is going to change. That means that point C will be moving in this direction. So if we want to calculate the hydrodynamics of that problem, we will have to do a ship lines plan, okay, according to the position of the centroid. That's too much work. So what we do is you simply say, okay, we take the reference system at midship. And yeah, we have to accept that the centroid is not there. And we have to include the term that we just discussed in the previous minutes. Okay, now we can, what's the next step? So this is the solution. It's a vector. This is the motion of the vertical displacement of the centroid. This is a rotation, since this is a rigid bar. Now, what we do is we say this is an amplitude for both and multiply by e to the I omega t. That's it. We replace it into here. We have something like this. This is going to be everybody replace into here and give me these 4 values of the dynamic matrix. Everybody. I want this, and that. 4 values for the dynamic matrix as function of omega. And right now, since we are working with free oscillation, we need to find omega. Once you have D11, raise your hand so I will write down whatever you want to tell me.
It will be K1 plus K2.
What about, see, this term here is being multiplied by W, and the first line forms this equation. So W is here and also here. So whatever you tell me, it has to be a combination of this term, some of these, and some of these too. So the 2 have to be in here. Manrique, do you have it?
I think so. Minus omega square the mass for the mass plus K1 plus K2.
Thank you. Yes, so this is this term after you replace this expression in here. Giovanna, there is somebody in the waiting room. The second one is this one here, right? You replace this into here, eliminate e to the I omega t, and the theta is here. So it's going to be simply K2b minus K1a. So this times W, this times theta equal to 0. That's the first equation. The second equation is this one here. So whatever goes here is multiplied by W. And you see that this is a term which is multiplied by W. So this goes here. So it's K2b minus K1a. And finally, this one here is Vega. What do we have for this space, for D22 here? What do we have for this? Miss Vega, can you hear me? Vega, no. Looks like we have problems with the connection with La Maná. Let's go up. Miss Astudillo, what do we have here for the D22 here?
Minus omega squared inertia plus K1 A squared plus K2 B squared.
There. Okay, so this is what we call the dynamic matrix. Remember, we like to put it like this because we recognize that we have here omega squared in this matrix. This is an homogeneous problem, easy to solve. What's the simplest solution for this problem? Tell me. Simplest solution for this problem, what is? Is the zero solution. Yeah, because if these two, W and theta amplitudes are zero, this and that are zero, that's the solution. So we want a different than zero solution. That's what we're looking for. That's what we call a non what? Jesus, why you are here? You're not supposed to be here. Supposed to be here. If we want a different than zero solution, then what we do is we simply take the determinant of this matrix equal to zero. In this way, it doesn't have inverse, and we avoid the solution being equal to zero. That's the only option that we have. So we said the determinant of D equal to zero. Look, this is an algebraic equation. Okay, you can plot it. You go like this. Oh, I'm sorry. There are only two roots. There are only two roots. So here and here we have the two roots of this equation. That means that if you have this, replace it into here, this matrix has no inverse. Since this has no inverse, you can allow these values to be different than zero. Okay? For any other option, okay, this matrix has determinant different than zero, so you can calculate the inverse. If you calculate the inverse and put it into here, the solution will give you zero. Okay, so these are the two options that you have, either this or that. That's the only things that you have. Now, what's the next step? The next step is to find or to express the amplitudes. And for that, we have a problem. Why? Because if we come back the equation that we had before, okay, we have here D omega squared. At the moment that you replace this frequency by one of these two, this matrix is singular. you can say that it is dependent, linearly dependent. That means that the first equation, only when you replace here one of the natural frequencies. Remember, in that case, the determinant is 0. So the first equation is equal to the second multiplied by a constant. So you cannot simultaneously. Okay, so right now, when you replace for one of these two values, the determinant of this is 0. So you cannot solve this system. What can we do? What we do is this, okay? Since the system is linearly dependent, we neglect or we forget about one of the equations. We accept we cannot calculate W and theta. Why not? Because there's not enough information. So we forget about the second equation. Now you say, hey, wait a minute. We have two unknowns and only one equation. We cannot solve it. I know. So we have to do something extra. And that something extra is and divide the whole system by one of the amplitudes. For example, let's divide this system of equation by W. So we're going to do two things here. The last equation is going to be neglected because it's linearly dependent from the others. System of equation, we divide it by W. So here we have, in this case, since we have two equations, we have the first term is going to be D11. The second one is going to be D12. Because the other two, we neglect them. And then the first term is going to be W divided by W, so that's equal to 1. And the second one is going to be theta divided by W. And on the right-hand side is equal to 0. Next, let me erase all of this. You can see that this is multiplied, this is known, this is 1. Multiplied by this one here, the result is something that you know, okay? This product does not include any unknown term. So you can move it to the right, since right now it's an independent term. So you can say that D12 multiplied by theta divided by W is equal to minus D11. Okay, and the only thing that differentiates this thing here is that there are two options. You can either replace this value or this one here. If you replace this one here, you are going to obtain a ratio of these amplitudes. If you replace the other, you're going to obtain a different value for this one. So here, you can say that theta over W equal to what? Minus D11 divided by D12. So remember that this one here, especially the D11, depends on omega. So you put here omega 1 and obtain one value. Put here omega 2 and obtain a different value. And that's the ratio between amplitudes. Ratio between amplitudes. Okay, so you, for example, if you had this expression you could say, for example, that theta equal to W times theta divided by W. Okay, you can say, I cancel this with that, and that's equal to that, yes. But the advantage of this is that this ratio, you can calculate them from the previous step. So you replace this into here. And that's an expression for W. But we said that we have two options, right? We have two options here. So what we can do is, since this is a linear problem, we can use one option, the one that we obtained when we replaced omega 0, 1, and then calculate this and we put it into here. And then we can do the same process with the second option, omega 0, 2. So we found a relationship between amplitudes according to the value omega that we're using. See, in this case, there are two options. In your homework, it's going to be three options. 1, 2, and 3. So you have to calculate three relationships. Now, do you remember how do we call this relation between amplitudes? Anybody? Anybody remember how we call this?
Shape mode. Mode shape.
Mode shapes, mode shapes. Mode shapes. I need one extra page. Let me reproduce this. Let me just a second, please be patient. An extra page. What happened? It doesn't record. Damn it. There's nothing recorded. Anyway. Okay, so let's suppose that we have everything. So, Jesus Christ. So, I need another color. So, we have two natural frequencies in this case, and two mode shapes. And in this linear analysis.
Doctor, you don't share screen.
Oh,
Yeah.
Jesus Christ. Yeah, you have to tell every time I do something wrong, tell me, please. Now you can you see what I'm?
Yes. Yes, doctor.
Thank you very much. Please don't hesitate. If there's something wrong, tell me, because otherwise we will waste time. Okay, thank you very much. So in this is a linear analysis. This is something that we have to have in mind, okay? This is linear analysis. We can superimpose them. So we can say that this is a very long expression, people. W of t, theta of t is equal to, we have one first equation, one first term, okay? This is a constant that we don't know. And then we have 1, and then here I have theta divided by W. But this is the result of using the first mode shape. And this is e to the I omega 0, 1 time plus a phase shift. They call it beta 1. And then we have something similar for the second mode shape. We say W2, similar to this one, but for the second mode shape. So it's going to be 1. And here I have theta divided by W, but for the second mode shape. Then e to the I omega 0, 2 time plus a phase shift. So these two are the mode shapes. And in here I have 1 and 2 natural frequencies. You come to the university in 3 weeks, we will do a free oscillation, and we can record the oscillation, and hopefully we will be able to identify, hopefully, at least 2 of the 3 natural frequencies. It's very difficult to find the 3, but let's try. Okay. In your homework, the one that I'm going to publish this afternoon, you are going to have to analyze a system with 3 degrees of freedom. Okay. So that's going to be something like this. Okay. So you're going to have something like this. So here it's like a building with 3 floors, 3 stories. Okay. And the thing is that if we have an earthquake, this is going to move. Okay. So this is something that we're going to impose is indirectly the excitation. Okay. So we're going to model this as a 3 degrees of freedom system. So we're going to have, this is going to move. This is our x of t. Okay. And the influence of this vertical, we call it legs. These are beams. Okay. They're going to contribute with stiffness and also damping. So this is M1, is basically this one here. And something similar for the second, and similarly for the third. Okay, so here we have 3 degrees of freedom, U1, U2, U3. In this case, in the real world, this is going to be U1, this is U2, this is going to be U3. Okay, so in our case, we're going to say, okay, this motion, x of t, is going to be imposed. So I know what x of t is. And we want to determine U1, U2, U3. So the first thing that you have to do is set up the differential equations for this case. And next step is to calculate the natural frequencies and mode shapes. And next week, we will review. It's very simple. If this is present and the damping is also present, we can recall how to calculate the response of the system. Questions, people? Any questions about this? Questions? No? Okay, no questions. Then please don't forget that you need to tell me if you want the class notes. And also you have to do this Excel training. Okay. For example, for all of this work, 3x3, it's a lot of Excel that you can be using. Okay. If you have enough skills in Excel, this module should not take you too long. But if you are on the other side and you have not enough skills of Excel, that will help you, especially if you are very close to graduation. Okay. That's a lot of calculations that we can do using Excel. And we don't want you to waste time, okay, trying to know how to do these things with Excel. Now you train, during the semester, you apply them and you save time. If there is no question, then I'll see you Tuesday. Have a nice weekend. Viva el Ecuador.
Thank you, doctor.